Before watching the next slides on Chapter 2, I want to go over a few more things about putting elements together to make compounds. We're going to talk about covalent molecules and ionic molecules. But what makes certain molecules come together to make compounds? This is actually coming from Chapter 7.1, so I'm just going to skip a little out of sequence for a minute just to give you a better idea where these things come from. So remember we said even though this is not what an atom looks like, it's a good way to think about things. So we have the the protons and the neutrons are in the nucleus, and the electrons are on the outside. So we're going to pretend they're kind of in shells like this. See, these are the negatively charged particles that are on the outside of the nucleus. The number of electrons always equals the number of protons, and they are assigned values or levels known as principal quantum numbers, which we'll get to in Chapter 6. And the ionization energy is the energy to remove this outermost electron. So you can see here the electrons on the outside. These outer electrons are called valence electrons, and this ionization energy is the energy required to remove them. So it is these valence electrons that are involved in bonding and these interactions and forming bonds and ions with other molecules. And we will see how this can actually explain some of the properties that we see. So we talked a little bit about the periodic table and how originally it was arranged according to mass, but as it turned out this was inadequate for higher order elements and it was not really accepted. Then Dmitri Mendeleev and Lothar Meyer looked at other ways of proving this recurrent periodicity. And he ordered the table of elements based on atomic mass had inconsistencies, so they went on to try to name it order it using atomic number. So the modern periodic table orders elements by atomic number, and we've talked about this in the early parts of Chapter 2. But now we're going to understand why this turns out to be. So this was the periodic table. We've used it in class so you understand where all this is coming from. We see all the different groups as you go across and going down. We're going to talk a little bit about them now. So you look at the atoms arranged according to increasing atomic number, you will notice that there are trends. As you go across what's called a period, you're increasing in atomic number, and you keep going across 8, 9, 10, 11. The next line would be 11, 12, 13 through 18, and the next line is going up. So the atomic number is going up, which means the number of protons is going up and the number of electrons is going up. So this is they're always in order. So each row is called a period as you go from left to right, and they're numbered. So you can see the period numbers here on the side, period 1, 2, 3, 4, 5. The atomic number is increasing, the number of electrons is increasing, the atomic radius is increasing, and this electronegativity that we were talking about, the amount of energy required to remove an electron, is also increasing. Then we can look at the vertical groups, up and down, or columns, what we call them groups. And the group number, you see on top here, the little group number 1A, 2, 2A. Those group numbers give the number of valence electrons for all the representative elements in that group. So these are the outermost electrons that are available for reaction. And elements in the same group has the same number of valence electrons, which means they will undergo similar types of reactions. So the alkali metals are in column 1. They have 1 valence electron. The number of the group is the number of valence electrons. The earth metals are in group 2, have 2 valence electrons. Then you go to the other side. The noble gases have 8 valence electrons. The halogens have 7 valence electrons. And 3, 4, 5, and 6 have respectively those valence electrons. So the group number can tell you right away how many valence electrons the atom has. We also talk about atomic radius, and that's really the measure of the center to center of 2 radii when they're together. If it's a covalent radius, it's half the radius distance between the adjacent nuclei. If it's metallic, it's more about how the structure is, which we'll talk about that actually in like Chapter 11. But atomic radii tends to increase going down and decrease going across the periodic table. So the numbers in the lower left-hand corner will be the biggest atoms. The ones in the upper right are going to be the smaller atoms. So let's start from the noble gases. These are actually very small. They have 8 valence electrons, and these are all considered filled shells. So they're very unreactive. They have 8, they want 8, they don't really react with anything. Conversely, on the other side of the periodic table, we have the group 1 elements, which are lithium, sodium, potassium, rubidium, cesium, francium. These are all the alkali metals, and they have one valence electron because they're in group 1. These have a low ionization energy. They have a tendency to want to give up this electron to form an ion. So it doesn't take a lot of energy to remove that one electron. And you can see the sizes here. Lithium is smaller, and as you're going down, they're getting bigger. And if you notice that here, back to this, if you look at the charge, the ion is smaller than the element with the electron. So when you move the electron, it actually gets smaller. If you look at group 7A, these have 7 valence electrons. They don't want to give up an electron. They have very high ionization energies. In fact, they want to take an electron from somebody else so that they can have the 8 and feel like the noble gases that have 8. So they tend to form what's called negative ions, such as F-, chlorine-. They want to form these negative ions. So you can see what can happen here. They come together. The group 7A elements come together with the group 1 elements and they form metal halides or salts. So sodium and chloride. Sodium gives up its electron, the chlorine picks up the electron, and you have the sodium chloride salt. So that's exactly what all the halogens do. A halogen means salt former, and these compounds tend to form salts. The group 2 elements now have 2 valence electrons, so they're going to tend to react with something that they can give their 2 electrons up to. So there'll either be something like oxygen, which has 6 valence electrons and wants 2, so they can exchange. Magnesium can give the 2 electrons over to oxygen. Magnesium becomes 2+, oxygen becomes 2-. Everybody's got 8 in their highest shell because magnesium just gave up its last 2, and these form magnesium oxide. Sometimes things can go together where they need 2 of the other ones. So magnesium reacts with chloride ions, and they only have 1 valence electron. So it will take 2 of them together with the magnesium. So magnesium each gives up, you see in the center here, magnesium gives up its 2 electrons, 1 to each chlorine atom, and makes magnesium chloride, which is MgCl2. So now you can start to see where these subscripts come from. So magnesium has 2 chloride atoms because it started out as having 2 valence electrons. And in some of the talks that we're going to talk about doing this crisscross thing, where you take the charge and you're going to crisscross it, and that's what your subscripts are going to be. And you're going to see that in the chapter 2 lectures. So basically, just to summarize this, so we can classify these elements based on their valence electrons, and these determine which elements react with which other elements on the periodic table. So we said that 7 and 1 go together, 2 and 6 go together, and 2 can go with 7, but you need 2 of them, and these kinds of things get put together. So I just hope this clarifies this just a little bit more for when you start looking at the rest of chapter 2. I didn't talk too much about the transition metals. Those are in between. Those you can't always tell what the number of valence electrons are, and that's when we will be using Roman numbers, or some way or another you'll be told which valence electron state that you're in. Okay, so just want you to remember some of the trends in the periodic table, going across and going down as far as atomic radii, and being able to look at the periodic table and pick out which is the smallest element, which is the largest element, which has the highest electronegativity, which has the lowest electronegativity. And we'll get into this more in depth and why these numbers are what they are when we finish chapter 7. But I just wanted to give you a little bit of background of why certain elements come together in certain proportions before you go on to chapter 2, which is talking about naming some of these elements, compounds. So this is just a precursor to that. So go ahead and watch the rest of the chapter 2 videos, and then we'll deal with all the naming nomenclature and how these all come together on Thursday. Okay? See you.